Well, hello class. In lesson 2.6, you'll learn to find the zeros of a function and also determine the multiplicity of a zero and the effect it has on the graph. Let's go over first what a zero is. A zero is simply the x-intercept of a function. It's identifying where the graph is going to cross the x-axis. So we could refer it as the x-intercept, we could refer it as the zero, and sometimes we also refer it as the roots. But again, they all mean the same thing. We're just simply looking for when a function is crossing the x-axis. Now, for polynomials specifically, the degree of the polynomial can determine how many times, the most number of times that the function will cross or have an x-intercept. So if we have a degree of 4, 4 would be the number of times that the polynomial will cross the x-axis. At most, it will not be greater than 4. It could be 4 or less. Now, if that degree is an even number, then it's going to cross the x-axis an even number of terms. So going back to the example I said, if we have our polynomial of f of x, and the highest exponent is x to the 4th power, and then we have a bunch of other terms right there, this polynomial can cross the x-axis no more than 4 times, or anything less than that. But because 4 is an even number, it could cross the x-axis 2 times or 0 times. So it's going to be, again, an even number of times, or in this situation, 0 times. However, if your polynomial is raised to an odd power, like 7, and again, we have all these other extra terms there, so we get to the constant, then this polynomial will cross the x-axis 7 times, or an odd number less than 7. 7 would be the most. So 7, 5, 3, 1, but an odd number of times. So 7, however, would be the largest number of times that we can cross the x-axis. So we're going to have, again, our intercepts, no more than 7 intercepts. Now, how do we find those intercepts? Well, the solution to the equation f of x is equal to 0 are called, again, the zeros of the functions. They're referred, again, as the roots. So if x minus c is a linear factor of the polynomial, then the 0 would be x is equal to c. It would equal to this value right here. So if we're subtracting x minus c, the 0 would be the value of c, this number here that we're subtracting. Now, every polynomial can be written as the product of its linear factors. So let's look at some examples of polynomials written as the product of linear factors, and let's use those linear factors to find the zeros to these polynomials. So for example, number 1 right here, to find the zeros of this function, we're again essentially trying to solve this equation. What's going to make this equal to 0? Well, since this is already in its linear factor form, that is simply answering the following question. What makes x equal 0? What makes x plus 4 equal to 0? And what makes x minus 5 equal to 0? Well, for the first one, it's already solved. X is equal to 0 by being equal to 0. But for the second one, x plus 4 is equal to 0 by having x equal to negative 4. And for the third one, x minus 5 is equal to 0 by having x equal to to positive 5. So the zeros to this polynomial are 0, negative 4, and 5, which is essentially the solution to the equation. So f of x is equal to 0 when x is equal to 0, negative 4, or 5, okay? So these are the two ways of thinking about this and answering the question, again, the zeros. So again, these are your zeros for this function. So let's see, try this example. Pause the video and then come back and check your work. So for this example here, negative x is equal to 0 when x is equal to 0. 2x plus 3 is equal to 0 by subtracting 3 to both sides and then dividing by 2, we end up with negative 3 over 2. And x minus 5 equals 0 by making x equal 5. So those are your zeros. And there you have them. Cool. Very, very cool. All right, let's look at example number 3. Let's see. Well, here, x plus 3 is 0 when x is equal to positive 3. 3x minus 5 equals 0 when x is equal to positive 5 divided by 3. And the last one is a little tricky one. So let's write it down. We have 7 minus 5x equals 0. And that's going to subtract the 7 to both sides. So that does give us negative 7. But since we're going to divide by negative 5, x would end up becoming positive 7 divided by 5. So the 3 zeros to this polynomial are 3, 5 over 2, and positive 7 over 5. All right, try this example, pause the video, and then come back and check your work. So let's check your answer. So x here equals to negative 3 over 5. X is equal to positive 7 over 4. And the third zero would be x equals to positive 5 over 9. Now when you submit your work on Edulastic, you'll only need to provide the zeros again. So simply type in again your list using a comma to separate each number. So make sure that you include again a comma in between each number and not just a space. Now, let's move on and let's discuss their multiplicity. The multiplicity of a zero is the degree of its corresponding linear factors, which simply means is the number of times x, the number of times again x is going to equal to this value. How many in other words, how many solutions this polynomial equation has. So for example, here we have a polynomial again in its factored form, and we have x minus 3 to the 5th power and x plus 5 to the 2nd power. And we want to figure out again what's going to make this thing equal to zeros. So if I look at x minus 3 and set this equal to 0, that means that x is equal to positive 3. So that's one of my zeros. X equals to positive 3. Now the multiplicity of this is the degree of its corresponding factor. So since the factor is x minus 3, the degree of that is 5. So that means that the multiplicity of x equals to 3 is 5. Now, what does this mean? Well, what this means is that the equation x is equal to 3 is going to be, the answer of x is equal to 3 is going to exist 5 times. So in this situation here, x is equal to 3 not only once, but a total of 5 times. And for the second factor of x plus 5 equals to 0, x equals negative 5, the multiplicity for that is 2. So what that means is that x is equal to negative 5 2 times. So this polynomial has a total of 7 solutions, 5 that are 3, and 2 solutions that are negative 5. So we have a total of 7 solutions here. And that's what the multiplicity means in terms of the number of solutions that this polynomial is going to have. So look, try this example here. What are the zeros and their respective multiplicity? So for the first one, let's check your work. Negative x to the 3rd power, well, I'm sorry, just negative x. Don't worry about the degree right now. So here, negative x is equal to 0 by having x just be 0. And x minus 3 equals to 0 by having x equal positive 3. So my two zeros are 0 and 3. The multiplicity of x equals 0 is 3, and the multiplicity of x equals 3 is 2. Now, what does this mean again in terms of solutions? That there's a total of 5 solutions, 5 total solutions, where 3 of them is the number 0, and 2 of them is the number 3. So x is equal to 0 2 times, and x equals 3, x equals 3 2 times, and x equals 0 3 times. Let's see, pause the video and figure out the zeros and the respective multiplicities. So let's look at the answer. Let's check your answer. So for the first one, x is equal to 0 has a multiplicity 5, and x equals to negative 7 over 3 has a multiplicity of 4. Again, pause the video, again, one more time, and then come back and check your work for this one. So for this example, x equals negative 7 over 2. That has a multiplicity of 7. And x equals to 1 over 5 has a multiplicity of 9. So 7 solutions, x will equal to this number of negative 7 over 2, and 9 times x equals to the fraction of 1 over 5. Now, these multiplicities also have an effect on the graph of our function. If the multiplicity of a 0 is an even number, then the graph is going to be tangent to the x-axis at that 0, which simply means, to be tangent means it's going to touch the x-axis. It's never going to actually intersect and go through the x-axis. It simply touches the x-axis at that one location for that one instant. Now, when the multiplicity is an odd number, 1, 3, 5, so on, the graph is actually going to intersect the x-axis at that 0. So for example, let's look at example 10 before we go to this one. Let's look at example 10. So right here. Here we have 3 zeros. We're touching or crossing the x-axis at 3 locations. Here, here, and here. So our 3 zeros, our 3 x-intercepts from left to right is x is equal to negative 2, x equals to 0, and x equals to positive 3. At these 2 locations here, at negative 2 and at positive 3, this is tangent to the x-axis. Notice again that the graph simply touches the x-axis and then turns around and bounces off and moves again and goes in the opposite direction. Because the graph is tangent at these x-intercepts at negative 2 and at positive 3, that means that the multiplicity of those numbers is going to be some even value. So the factor of x plus 2 and x minus 3 are being raised to some even power. Like, for example, they might be raised to the power of 2, or they may be raised to the power of 4. And x minus 3, the same thing. It might be raised to the power of 4 or power of 6. Or maybe that power is 8. Okay? We don't know what specifically what number that is, but we do know, again, because of the way it behaves on the graph, that it's going to be some even number. Not necessarily this specific even number, but it's going to be some even number. Now, because of the number of times that it turns, 1, 2, 3, and 4, I know that these exponents and the degree of this has to be less than that value. It has to be 1 unit higher. So it cannot be more than that. So these numbers actually are going to have to add up to 1, 2, 3, up to 4 times. Okay, so the numbers have to add up to 4 somehow. But again, we're not going to go into actually figuring out what that value is. We're just going to, again, understand that because of their multiplicity, that again, that's going to be an even number of times that x is going to equal to negative 2, and there's going to be an even number of times that x is going to equal to 3. What that number is, again, we're not going to worry about today. And for the middle one, this one right here, because it actually intersects and actually goes through the x-axis at 0, that means that the multiplicity of this of 0 is going to be some odd number. So here, x minus 0, just simply x, is going to be raised to some odd power, like 1 or 3, 5, 7, again, some odd exponent. Okay. So let's use this idea now to determine the zeros, the multiplicity, and again, the effect it's going to have on the graph. And then we'll just draw a simple sketch of this. So let's see. So from left to right, the first zero is x is equal to 1 and has a multiplicity of 2. The second zero is positive 3 over 2, and that has a multiplicity of 2 as well. And the last zero is negative 4, and that has a multiplicity of 1. Since there's no exponent there, that's an invisible 1, so it's understood to be 1. Now, what's going to be the effect on the graph? Well, the effect on the graph is that at 1 and at 3 over 2, because their multiplicity is an even number, 2, it's going to be tangent to the x-axis. So it's simply going to touch the x-axis and then just simply turn around. But at negative 4, since the multiplicity is 1, it's going to actually intersect and actually move through the x-axis, and it's going to intersect the x-axis. So to draw a rough sketch of this graph, let's draw a horizontal line in my y-axis just to separate the positive side from the negative side. We have an x-intercept at negative 4. We have an x-intercept at positive 1. And then we have another x-intercept at 3 over 2, which is 1/2, 1.5. So 3 over 2 right there. So the graph is going to intersect at negative 4. So let's say that the graph starts down here. It's going to go up, turn around, reach a maximum height, start turning around because it needs to touch at 1. It's going to touch, be tangent on the x-axis at 1, move up again, move down, and be tangent again at 1, and then simply move in the opposite direction. Now these curves, again, it's a polynomial, so these should be, again, a smooth curve. So let me try to draw this a little bit better. There, okay? It shouldn't be a very big gap right here. But again, it should be smooth. It shouldn't have, again, sharp turns because it's a polynomial function. It should be a nice smooth curve. And this is the effect that the graph will look like, okay? We're intersecting. The zeros are, again, 1, 3 over 2, and negative 4. So from left to right, that would put negative 4 on the far left. 1 is smaller than 3 over 2. And since these numbers add up to 5, this is going to behave like the function, like the power function, x to the 5th power, which again starts at the bottom and moves up. So that's how I know that the graph is going to start down here, move upwards right here, intersect the x-axis at 4, reach a relative max, decrease, tangent at 1, tangent at 3 over 2, and again change direction and continue to increase again and have the same end behavior as x to the 5th power. And the reason, again, it's x to the 5th power, because if I multiply all of these together, like if I multiply x minus 1 times itself, 2x minus 3 times itself, and x plus 1, that's going to end up giving me a total of x to the 5th power. Simply adding the exponents tells me that's x to the 5th power. So it's going to behave exactly like an x to the 5th power polynomial. So the end behaviors are going to be like this. They have to be pointing in that direction. All right, well, there you have it. That concludes, again, the examples on this section of 2.6, zeros and their multiplicities. If you do have any questions, please send me a message on Remind or through email. I appreciate you watching, and I hope you have a great day. Goodbye.